Okay, great. So last time we stopped over here, and today we'll be looking more into the relationship of primal and dual LPP problems, and in particular, we'll be studying about three main theorems, which are more or less very important. After that, once we have the theorems out of our way, we will be looking into complementary slackness condition and why is it important. Okay. So let's begin with the first theorem, which is the weak duality theorem. Okay, and the weak duality theorem basically states that if you have a maximization primal LPP problem, then every feasible solution, okay, to the dual has an objective function value greater than or equal to every feasible solution to the primal. Now, what does that mean? Let's look at this through an example. Okay, let me get my pen. Where's my pen? Okay. So assume that this is our primal. This is an example that we have also looked at before. So this is the primal LPP, and we already saw how to convert this into its dual. Okay, so this is basically, so we had two decision variables. So you will have two constraints, and you have two constraints here. So you will have two decision variables over there. So let's say that this objective function is Z, and we call this guy W. Okay, this is a W. All right. Now, what we want to do is we want to plug in different values for, say, the primal. Let's look at the primal first. Look at this guy. So we want to find different values for x1 and x2 such that these two constraints are satisfied. So I have taken 0, 0, obviously 0, 0. If you plug into these constraints, you would see that 0 would be less than equal to 5, and obviously 0 would be less than equal to 12, okay? And so it would give us a objective value of z is equal to 0. And now let's look at some other values. So for example, if I plug in 3 and 1, again, you would see that 3 plus 1 is 4, 4 is less than equal to 5. 3 times 3 is 9, plus 2 is equal to 11. 11 is less than equal to 12. So these two constraints are satisfied, and it would give us an objective function value of 23. And we can keep doing this until we reach the optimal feasible solution. Okay, so this is for the primal. Now let's do the same thing for the dual. In case of dual, you cannot put 0, 0 because 0 is not greater than equal to 6. So you have to start with some non-negative and non-zero value. It obviously will be not negative because y1, y2 should be greater or equal to 0. It cannot be 0 because otherwise these two guys would not be satisfied, right? So let's start with 3, 3. If you put 3, 3, you would see that these two constraints are satisfied, and you would get an objective value of W is equal to 51. Then you put another value, say 2, 1. Again, it satisfied these two constraints, and your objective value further reduces. I mean, as you see, this is a minimized. So obviously, it should be going in the down direction. And since this is maximized, it should be increasing. All right. Now, one thing that you have to notice, something very interesting, is that in the primal, we are moving from low value and we are trying to get some higher value. You see 0 is getting to 23, and obviously probably the next number will be greater than 23 and so forth. In its dual, we are going from a very high value and we are going down. So if there is an optimal solution, okay, so what the dual is doing is dual is moving from up to down, from some high value to down. So it's kind of an upper bound. And the primal is moving from down to up towards the optimal solution. We call this the optimal solution. Is it clear? Does everyone understand what I'm trying to say?
So in the end, they both should get to the 1 point, right?
There is a condition until which at which if that condition is satisfied, then the dual and primal will give us the same optimal solution. Yes. So there is a condition. There's a dual gap which I'll be talking about today. But for now, do you understand what I'm trying to say? So the primal is trying to go towards the dual from bottom. I'm sorry, the primal is trying to go towards the optimal solution from the bottom, and the dual is trying to get to the optimal solution from top. So it is upper bounded, and this primal is a lower bound. Is it clear?
Yes.
Everyone?
Yes.
Good. So basically, if you see this, and now you go back to the definition of our weak duality theorem, it says that if for a maxima, so we say that our primal is assuming it's maximization, okay? So we have written it in the canonical or standard form. If if a primal LPP is a maximization problem, then every feasible solution to the corresponding dual, okay, will give us an objective value, which was, which would give us an objective functional value, which was the W that we wrote over here. And this would be always greater than or equal to every solution, every feasible solution in the primal. That if you compare 51, 51 would be always greater than or equal to every solution you get in the primal, okay? So you can keep doing this, find all the feasible points, and you see that whatever value you get here will always be less than 51. Whatever value you get here will always be less than 29. Whatever value you get here will always be less than any value you get in the dual. Okay, so this is basically what the weak duality theorem is telling us. So if I want to write it in verse, W will always be greater equal to Z. The W is the objective functional value of the dual, and Z is the objective functional value of the primal. Is it clear?
Yes.
Good. So now that we have the weak duality theorem in place and we have understood it, okay, let's try to prove it. The proof is again something very straightforward. And if actually you have understood how we obtain the dual of a primal, then we introduced the concept of duality, we actually use this there. But I'll try to refresh your memory, so I'm going to do it again. So let's assume that for the primal, for this guy, x1 and x2 are the feasible solutions. Okay, so one of these, so these sets that we got over here, 0, 0, 3, 1, and all these are all feasible solutions for this primal problem, LPP. So let's take one of them. Let's say x1 and x2 is a feasible solution for the primal. Okay, that means, what does it mean? It means that if I plug in x1 and x2 into the constraints, it would satisfy the constraints. That means these two hold, right? Am I right?
Yes, that's right.
Good. Oh, I need to clear everything. Okay, so what happens then, and also it means that now if you look at the dual, let's go back to the dual. So this guy is the dual, okay? And in the dual, what do we have? In the dual, we have an objective function 5y1 plus 12y2 and two constraints over there. So now in the dual, what I do is, what happens, so this 5, if you look at this 5 over here, okay, is basically this 5, right? And what I'm saying is, I'm saying x1 plus x2 is less than equal to 5, okay? Now, if I replace or I substitute x1 plus x2 less than equal to 5 in place of this 5, it would mean that my W would be greater than equal to, in place of 5, I write x1 plus x2 times y1 plus, in place of 12, I write this 3x1 plus 2x2 y2. Can I do that? And W obviously will be greater than equal to. Am I right? Is it clear? Yes. Everyone understand what I've done? So basically what I did is I took these two equations and I substituted it into the objective value of the dual. So I would get W would be greater than equal to, why greater than equal to? Because in the primal it was less than equal to 5. So now it will become greater than equal to, I just substitute in place of 5, these two terms. And now I rearrange this equation in terms of x1 and x2. So I put, I factorize everything in terms of x1 and x2, and I would get this guy, okay? Now, we know that, okay, y1 and y2 are also feasible solutions to the to this guy, to the dual. So let's take any one of these pairs, and they are all feasible solutions to the dual. Let's say we just arbitrarily choose one, say y1 and y2, and they are solutions to the dual. And therefore, since y1 and y2 are the, feasible solutions to the dual, what we would have is these two constraints would be true, right? This constraint greater than equal to 6 and this one greater than equal to 5. So since this is this, and then what happens is in place of this, so this also appears in this equation that we rearranged earlier. So in place of this, I just write 6. So I replace this guy with 6, I replace this guy with 5, and I would get W is greater than equal to 6x plus 5x2. And what is the 6x plus 5x2? It turns out to be the objective functional value of the primal. It was our Z. So this tells us that W is greater than equal to Z. And therefore, I proved the weak duality theorem as we discussed. So I proved that every feasible solution to the dual will always be an upper bound on the objective functional value of the primal. Okay? Is it clear, everyone?
Clear.
Any questions?
Yes.
Any questions? Should I ask questions?
I have a question.
Yes, sir.
Remember the moment you substituted the x1 x2 less than 5 and 3x1 plus 2x2 less than 12 into the equation down below, and you made it like W is greater than the equation. In order to do that, both of the equations above should be of the same symbol? Like
yes,
so
I told you, yes. So we assumed that we have written them in the standard form for a primal, which was maximized. And I told you if it's maximized, the desirable symbol is less than equal to in our last session. If it's minimized, the desired symbol is greater than equal to. Okay, so if we have this in our standard form, we are assuming we are working out from a standard form, okay? And if you have this in the standard form, then you would get this. And it doesn't matter, actually. Even if you have any other sign, you can always convert it into the standard form and you would get the same conclusion, okay?
Yeah, okay, that's clear. Thank you.
Good. Okay, with that said, now let's get to the second theorem, which is the optimality criteria theorem. And this is the theorem, which is kind of an extension of the previous theorem, which is the weak duality theorem. So this theorem says that if we assume that if you're given that the primal and the dual have feasible solutions such that there exists a value or a pair of values, like we saw over here, okay, these values, these pairs, for which W would become equal to Z, okay? That means I keep going down over here and I get to some point, some pair, which would give me some Z value. Okay, let's call it Z star. And over here, I keep moving till I get some pair, which would give me some W star value, such that the Z star value, okay, is equal to the W star value. Okay, in that case, this value or this pair would always be the optimal solution to the dual, and the corresponding pair would be the optimal solution to the primal. Okay, so that means these guys will have the same optimal solutions. Okay, this is, as I said, just generalizing the previous, where is it? Yes, it's just a generalization, extension, not generalization, extension of the previous theorem. So let me give you an example of what I mean. So let's say that 2, 3. So let's go back here, over here. For the primal, if you put in 2, 3, what would be Z value? X1 is 2, X2 is 3.
27?
Yes, so Z would be equal to 27, right? Now, and what happens if you put 3, 1 over here for the dual, subjective function? Y1 is equal to 3, Y2 is 27. Good. So we see that there exists a pair, there exists some feasible solution for which the primal and the dual are reaching the same value. And the thing is that now, at this point, so there would, since the Z of the primal is equal to the W of the dual, there will be no other feasible solution in the primal such that the value of the objective function for the primal would be what we say greater than that of the W, that of W. So what I'm trying to say is, so over here we got W star is equal to 27, okay? And over here we got Z star is equal to 27. So what I'm trying, and we know that by the weak duality theorem, W should always be greater or equal to Z, okay? Right? So now there exists, so what I'm trying to say that there will, so if I keep finding or if I keep moving down, there will exist no pair up to a feasible pair such that it would further increase the value of Z star, because if it further increases the value of Z star, it means that the W would become less than Z star, which violates our weak duality theorem. Okay, so that means we have reached a point where from up and from down, we have reached one single point, optimal point, and this optimal point will be the solution, optimal solution to both dual and primal. If other than this, then this would violate our weak duality theorem, and therefore that is not an optimal solution. And when I say that's not an optimal solution, it means that either one of the problem was unbounded or it is an infeasible LPP problem. Okay, so we have to make sure that our solution is, our LPP problem has an optimal solution. Okay, even if it's unbounded, either the primal or the dual is unbounded, we would have such a solution, that such a case which would violate the weak duality theorem, and therefore it would not hold. So the weak duality theorem and LPP problem hold only when we have optimal solutions, not unbounded and not infeasible. Okay, is it clear?
Clear.
Good. Well, basically that's it. So obviously I found a point 2,3 for the primal, and I found this point 3,1 for the dual. And we saw that for both cases, they gave us 27, and this would tell us the optimality criteria theorem. And this tells me that 27 is the optimal solution for both primal and dual, and there's no solution better than this, okay? If there were a better solution, it means that the W greater than equal to Z condition would be violated, and therefore that problem that you're solving is either unbounded or is infeasible. That's why you are able to violate the weak duality theorem. Now, so I've explained the same thing over here, so you can just go through this in your lecture slides, this guy, okay? That's it. Let's go to theorem 3. Okay, in theorem 3 is the main duality theorem, which actually generalizes the previous two theorems, and it's giving you a general theorem. Now it's telling you that if the dual and the prime have feasible solutions, okay, then their optimal solutions will always be this. So if I want to find it, it means that if I give you a primal LPP problem, okay, I ask you to solve it. Okay, say I ask you to solve it using simplex method. Then I ask you to find the dual, and I ask you to solve it. Okay, and I do not specify how to solve it. Okay, some of you may again use the simplex method to solve the dual, but that would be a very wrong way to go for it, because using this theorem number 3, which is the main duality theorem, once I find the optimal solution for my primal, without any hesitation, I can claim that based on theorem 3, this would also be the optimal solution for the dual, okay? As long as I have found the dual correctly, okay? So and actually today I will show you another interesting thing is actually when you're solving the primal problem using the simplex method, in the last iteration where you find the optimal solution, the last iteration will also give you the optimal solution for the dual. And you can see it. So far we haven't seen it because we didn't know what a dual was. But today in an example, I'll show you exactly how this is. And therefore, in the exam, if I say solve the dual, you do not have to write the simplex table again. In the first simplex table that you used to solve the primal, in the last iteration, it will already give you, it will by default give you the solution for the dual as well. Okay, that we will see once we know what is the complementary slackness condition. Okay, so is this clear? So it's saying that if the primal and dual are feasible solutions, then both have optimal solutions where Z1 would be equal to Z star would be equal to W star. Okay, so this basically just generalizes the previous two theorems. Now, the thing that is very important for today's lecture is this complementary slackness condition. And I want you to pay attention to this and understand it carefully, okay? Let's say that we have a primal LPP, okay? We have its dual, and X star is the optimal solution for the primal, and Y star is the optimal solution for the dual. Okay, when I say Y star, it means the pair or the tuple of optimal values for the decision variables in the dual, and X star is actually, it's a vector, okay, where every element is a decision variable, and the values of these decision variables are the values that give us the optimal solutions. X star is the optimal values of the decision variables in the primal. Y star are the optimal values of the decision variables in the dual problem. Okay, so I'm saying that if I know these optimal values, these pairs for the decision variables, okay, in both the primal and the dual, then I can very easily say that this holds. That means X star dot, so dot product dot V bar over here. When I write V bar, it's a vector, okay, plus Y star dot U bar is equal to 0. Now, what is V and U? V and U are the vectors of the slack variables that we introduced. So the U vector is the vector of slack variables in the primal, and V is the vector of slack variables in the dual. So U is for primal, I denoted by P, and V is for dual. Okay, that's a D. Okay, so what I'm saying is if I take the optimal solutions for the primal and multiply it into the slack variables of the dual, plus I take the optimal solutions of the dual, multiply it into the slack variables of the primal, it would always be equal to 0. Clear? Now we will show how this is through an example. So since this is a dot product, these are vectors, so I can write it in a scalar form as a summation, right? I can say it's that summation of all xi's dot vi's plus summation over j of all yj's over uj's would be equal to 0. I here denotes the number of variables in the primal. And since the number of variables, so let's say that I is equal to, there are n variables in the primal, okay, from 1 to n. And we already know that if there are n decision variables in the primal, there will be n constraints in the corresponding dual. And for every constraint in the corresponding dual, we will be having a slack variable, because in the dual, the standard form is greater than equal to, right? So when it's greater than equal to, you have to reduce or minus some variable on the left-hand side to make it an equality, right? So we are adding one slack variable for every constraint in the dual. So if there are n variables in the primal, there will be n slack variables in the dual. Okay, and that is why we have VI, where V denotes the slack variables in the dual. Similarly, if you have m variables in the dual, you will be having m constraints in the primal, and for every constraint, there will be a slack variable, and that's why you have it indexed over j. Okay, so for j, it goes from 1 to m. Okay, so where n over here is the number of variables in the primal, and m over here is the number of variables in the dual. Do you understand this? Is it clear?
For now, clear.
Yes, so make sure that do not confuse between V and U, okay? So I've explained it. So, and since we have this condition, that means the optimal solution, the variables X star, Y star, and UV, which are the slack variables, we have always seen that they should always be greater than equal to 0. This is the constraint on the decision variables. And therefore, for every I, the product of this, in order to have this to be equal to 0, it means that the product of this should be equal to 0, and the product of this should be equal to 0. Okay, that means either one of these elements should always be equal to 0. All right, now we will show what this means again. Okay, so I said if I denotes a number, I just explained what I and j are. So this is the same explanation. Again, this is the same thing. Let's move. Okay, this is important. Look at this guy. So what does this condition tell me? That summation is equal to 0. This condition tells me that when you have at the optimal solution, that means when you have reached a point where the optimal solution is obtained, if a particular, so we already studied about what are the basic variables and what are the non-basic variables. Do you remember that in the simplex table?
Yeah.
Okay, so it says that at the optimal. So for example, in the simplex table, when you come to the very last iteration where you find your optimal solution, it says that if a particular primal variable, decision variable, let's say xi, we are talking about decision variables, not slack variables. If a decision variable in the primal, denoted by xi, is a basic variable, okay, that means it's a basic variable and not a non-basic variable, then obviously if it's a basic variable, it will take a non-negative value, okay? And then the corresponding dual will always be equal to 0. I'm sorry, the corresponding dual slack variable will always be equal to 0, okay? So if in the primal, the decision variable xi is basic, okay, then its corresponding dual slack will be equal to 0, okay? Similarly, if the dual decision variable yj is basic, then the corresponding primal slack will be equal to 0. Basically, what it's trying to say is trying to say the same thing that I told you over here. Either one of these two will always be equal to 0 at optimality. Okay, either this will be equal to 0 or this will be equal to 0. This will be equal to 0 or this will be equal to 0. Condition that xi, yj is the, I mean, we are at the optimal state. That means the last iteration of the simplex table. All right. So this is basically the complementary slackness condition. And I'll tell you why it is important. Actually, I already told you why it's important, because it helps you find the solution of the dual without having to solve it, as long as you know the primal, okay? Now let's apply it to an example. Let's look at it in an example, and by writing it down, actually, it may help you imagine what it means, okay? Let's go back to our example, which we always use, that we have used this before. This is in this. This was in the standard form where we had maximized subject to less than equal to. To make it equal to, I'm trying to solve the simplex table, right? To make it equal to, what I have to do is, before it was less than equal to make it equal to, I add a slack, and I told you the u's are the slack variables for the primal, and the v's are the slack variables for the dual. So to make it equal to, I add some value, which is u1, and I add some value, which is u2. So we have two slack variables for our primal, u1 and u2, okay, and obviously they should be greater than equal to 0. We know the dual of this equation, we have already solved it. Over there, we had greater than equal to. To make it equal to, what you do is you have to subtract something from the left-hand side, which is our v variable. So v1 and v2 are the slack variables for the dual, right? So now I have put this in the form where now I can actually tabulate the simplex table, and I can solve, okay? But I do not want to do that. I just want to show you what this condition, which we saw over here, means. This summation is equal to 0, okay? So with that said, let's assume that we know the optimal solution for this problem. We already found out that at x1 equal to 2 and x2 is equal to 3, z would have the maximum value of 27, okay? And also for the optimal solution of the dual, we saw that at 3 and 1, we would get 27. Okay, so we already saw this in our previous example. Now what we do is, let's write it down, okay? Let's write x1, which is over here. Let me bring my pen. x1 is equal to 2. This was our optimal solution. x2 is equal to 3, and z is equal to 7. We write it over here. Similarly, y1 is equal to 3, y2 is equal to 1, w is equal to 27. So based on our complementary slackless condition, it tells me that if x1 and x2 are basic variables, you see that they are basic variables, they are non-zero, right? Their corresponding dual slack variables would be 0, right? That means if you go back to the condition over here, that means since x1 is multiplied by the slack variables of the dual, so that means the v's should always be equal to 0, because the x's over here are not equal to 0, okay? And actually, if you solve this using simplex and you solve this dual using simplex, you would see that in the end, okay, even if you didn't know this complementary slackless condition, in the end, y1, y2, I'm sorry, u1, u2, v1, v2 would always be equal to 0. So these would be our non-basic variables, okay? So since x1, x2 are our basic variables, they are non-negative. Therefore, the corresponding dual slacks, that means v1 and v2, should be equal to 0. So when I multiply x1 times v1, it would be equal to 0. x2 times v2 would also be equal to 0. Similarly, since y1 and y2 are the basic variables in the dual, their corresponding slack variables in the primal should be equal to 0. And we see u1 is equal to 0, u2 is equal to 0. And with this condition said, we see that actually the complementary slackness condition holds. Okay? Is it clear?
Yeah.
For you guys to understand this better, what I suggest you do is solve this problem, the primal problem using simplex. Okay, see what are the values for x1, x2, u1, and u2. Okay, solve the dual using again simplex and see what are the values for y1, y2, v1, and v2. Then draw this table and you would get the same. You would see that actually this condition holds. When does it hold? It only holds at optimality when W and Z are equal. Okay, it will not be the same in any intermediate step or iteration of the simplex method. It will only hold for the final iteration of the simplex method. Keep that in mind. All right. Now let's apply the slackness condition to another problem. Let's say we have this problem over here, where this is our primal. This is objective function, and we have three constraints. So there are two variables over here, x1 and x2. So obviously there'll be two constraints in the dual, and therefore there'll be two dual slack variables. Okay, so there'll be v1 and v2. So similarly, we have three constraints. So there'll be three variables in the dual. And since there are three variables in the dual, there will be three slack variables for the prime. Okay. Now, let's say that u1, u2, and u3 are the slack variables for the prime, okay? And v1, v2 are for the dual, because there are two constraints and three constraints over here. Well, I use slack and surplus interchangeably. Actually, surplus variable because we are actually reducing something over here. So it's just, let's use the same word as slack. Okay, slack means that additional variable that I add in order to make the constraint equations equality. Change the sign to equality. Now, we have actually solved this problem before. If you look in your previous lecture, we have solved this problem and we have found that the optimal solution to this primal is at 6, 6. That means x1 is equal to 6, x2 is equal to 6. And over here, you see that our u3, that means the slack variable for the third constraint, is also equal to 6, okay? It's not 0. So this is also a basic variable, all right? And this would give us our optimal value of z equal to 42. Okay, look back to our lectures, previous lectures, and you see that we have solved this and we have got the solution. Okay. Now, also we know that the optimal solution, if you solve the dual to obtain the dual, you can convert it into the dual, and when you solve the dual, you'll see that the optimal solution would be at y1, y2 is equal to 1, 1. All right. And so if you write it down, so I write down x1 is equal to 6, x2 is equal to 6, x3 is equal, u3 is equal to 6, and u1, u2 would be equal to 0. These are non-basic. And similarly, y1 would be equal to 0, y2 would be equal to 0. We see y3 over here is equal to 0. y1 and y2 are non-zero. Okay. So what we see, what do we see over here? So this, what I have marked and highlighted in red, is actually what I have stated in the next statement. It tells me that there exists a primal slack variable, which is u3, which is on the basis because it's non-negative, okay? And it has a corresponding dual decision, which is non-basic. That means the dual decision, which is y3, the decision variable in the dual problem, would be non-basic, which will have a value of 0. So now what we do is, so basically what I can do is, this was assuming that we know the solutions, optimal solutions to both primal and dual. Assume that we do not know the optimal solution for the dual. We only know the optimal solution for the primal. And this is where actually this complementary slackness condition comes into play. So I know the optimal solution to the primal. I know what are the basic variables, the non-basic variables, okay? And I know the optimal value of Z. And I know that, and I do not know what are the values of y1 and y2 in my dual, okay? So assume that we do not know the optimal solution to the dual, and only when I say we do not know the optimal solution to the dual, it means we do not know the basic variables, the basic feasible solution to that, okay? So using the complementary slackness condition, what do we do? So we know this. So I know that x1 and x2 are non-negative. They are the basic variables. So their corresponding slack variables in the dual, slack dual variables would be non-basic. and would be equal to 0, therefore, since they are non-basic. Therefore, V1 and V2 would obviously be equal to 0. And over here, I know that since this is the basic, so the non-basic variables would be U1 and U2, and they are equal to 0. Therefore, in the dual, the corresponding decision variables, okay, the corresponding basic variables, because they are non-negative, would be Y1 and Y2. So since these two are equal to 0, it tells me that both Y1 and Y2 will be not equal to 0, and they will be the basic variables. Because we know by solving the primal, we found that U1 and U2 is equal to 0. So I can claim this step, knowing this step, using the complementary slackness condition. Is it clear? So all I need to know is this step. And then from this step, I can easily tell you what are the basic and non-basic feasible solutions in the dual. Because I know that in the primal, I found the basic feasible solutions, X1 and X2. So their corresponding dual slacks would be 0, which is here. And since they are 0, they'll be non-basic. They will be not playing any role in finding the solution, optimal solution of the optimal value of the objective function. And since I know that the slacks are equal to 0, that means these are non-basic, and therefore their corresponding decision variables in the dual will be basic, and both of them will be non-negative. How do I find, okay, you told me that they are non-negative, but what are their exact values, right? That may be your question now. One way to do that is, so this basically just tells me that which one of the decision variables are basic and which one are non-basic, all right? And as you see over here, Y3 would be, so this is going back to the previous question. So in this question over here, in this previous example, you see that Y3 was what? 0. Okay, so it was a non-basic. Why? Because its corresponding slack variable in the primal was a basic. Okay, because it has not 0. So this is the kind of information that, for example, if I had only solved this first guy, and I ask you to find the solution of the dual, the values for the slack variables and the decision variables in the dual, you can use this complementary slackness condition to find this. X1, X2 were basic, so their corresponding dual slack would be 0. U1, U2 were non-basic because they were 0, so corresponding would be non-0. And since U3, which is a slack in the primal, is a basic, it's non-negative, therefore its corresponding decision variable in the dual would be equal to 0. So Y3 would be a non-basic variable. So this is the relation I can infer from solving of the primal solution. Okay, and using this complementary slackness condition. Is it clear, guys?
Yeah.
Good, good, very good. Okay, so now I want to mathematically try to again connect the dual and the primal and tell you what does it mean. I mean, why I want to give you another perspective of how to look at the relation between these two, how these two are related. Let's go back to our, again, classic example over here, okay? So this is our example. And we know that the solution to this is this guy given over here. And we know it's dual, and we know that the solution to the dual is also this, okay? Now, what I want to do is, let's say I add, so I know that X1 and X2, because they are non-negative, 2 and 3, are our basic feasible solutions to this optimal value of C, right? So there's no value other than X1 and X2 that would maximize the value of C. So this is our optimal solution. So assuming that they remain the basic feasible solution, say that I add some very, very small value, say delta, to the right-hand side of this, to the first constraint, okay? So I'm adding 5 by some very small delta value such that X1 and X2 still remain as our feasible solution. They don't change, okay? Now, what I want to do is, now with that done, let's now solve this problem. Okay, so what I've done is take the first constraint, add some value delta such that X1 and X2 still remain as our optimal solution. They do not change, all right? And now let's see how, and I solve these two constraints. That means I take equation 1 and 2, and I solve for X1 and X2. So what I do is I say X1 plus X2 is equal to 5 plus delta. 3X1 plus 2X2 is equal to 12. And I solve these two. So I'll get X1 is equal to this in terms of delta, and X2 is equal to this in terms of delta. I substitute X1 and X2 in our objective function, the Z, and I get the value for Z is equal to this, okay? Is it clear what I've done?
Yep.
Okay.
Clear.
So now what I want you to pay attention is look at this coefficient in the z objective function, the coefficient of delta. We have plus 3 delta, right? So take a look at this 3 in the objective function. Now, do you think that this 3 is any way related to this 3 that we have as a solution in the dual? The optimal value for y1? Or in other words, let me say, if I, instead of adding plus delta over here, I cancel this and I add a plus delta over here. And I again solve these equations and I substitute in z, would I get an extra term in z where I would have plus 1 times delta, which would be the solution to y2?
Yes, so it will be plus delta.
Yes. So the first constraint, if I increase the value of it would actually give me or relate me to the solution of the first decision variable in dual. If I add this delta to the second constraint in the primal, it would somehow relate me to the solution of the second variable in the dual. How about if instead of plus, I write minus? 5 minus delta. What would happen? So instead of this guy, I've just written 5 minus delta and I solve those things. So will I get minus 3 delta?
I think no.
I think yes.
Really?
Duh. Try. Even if you minus delta or minus 12, 12 minus delta, you solve it for these two, you will see that in your z, instead of the plus, you will get a minus 3 delta. And again, it relates to, pay attention, the solutions over here cannot be, y1, y2 cannot be negative. Okay, I'm not saying that this will be minus 3, no. Minus 3, only you take the magnitude and you'll see that magnitude will be the same as the magnitude of the decision variable. Now, what does that minus sign indicate? I'm going to tell you over here. Okay, so did you understand? So by increasing, so let's say that we have these constraints. And so these, the things on the right-hand side, there are some resources. Okay, say there are some resources. So I'm saying that if I increase the resource, okay, one of the resources by some very little value, what would be the rate of increase of my objective function? So basically the solutions to your dual decision variables, the optimal values, is indicating the rate of increase or decrease of the rate of the rate of change. Sorry, the rate of change. So y1 or y2, okay, or this coefficient shows you the rate of change of the objective function of the primal. That means how much does the primal, the objective function in your primal change? Change means either increase or decrease. If I increase or decrease one of the resources. Okay, so for example, if I want to put it in an example, suppose that I have 5 over here denotes the number of hours or time that you have in order to produce a product 1 and product 2. Okay, x1, x2 are 2 types of products, and 5 is the amount of time you can spend on that. Okay, so saying that if I increase 5, say for example by some delta, small value delta, okay, it tells me that by increasing this by some delta value, I can actually, the number of products that I can make in addition to, so the more number of products, that additional number of products that I can produce is 3. Okay?
Okay.
So this is telling me that by increasing the value of the resource, it tells me how much does this affect the rate of change in the objective value. Okay, so basically, this is again telling me the solution of my dual problem. Isn't this interesting?
Applicable only in the case when delta is very small.
Delta can be, okay, this is a very good question. This holds only when x1, x2, y1, y2 are optimal. So that means only when we are in the optimal state, when we have found the optimal solution. That means at the point where both these guys meet at the same point. Any point in between, it doesn't work. Only at the optimal solution of the primal and dual does this hold. Okay?
But the
Keep
delta
that in
can
mind,
be
because
like,
I've written over here at the optimal solution. No other point.
Okay.
That's why I put a star.
but then delta can be like, not even the small, it can be like 1 or 2, right?
It can be, yes. And it can be also negative. So I want to tell you the marginal value, the marginal value means that if I marginally try to change the resource without changing, without making any of these non-basic, okay, that means X1 and X2 should be basic, okay? As long as they remain basic, and as long as they remain basic, if I can change my resource by either increasing or decreasing, that would tell me that the rate at which I can actually increase or I can produce more products, which is given in my objective value, objective function. Okay.
Yeah, that's very handy.
This is interesting. This is LPP, and this is actually the magic of LPP, because it helps you do so many things. Okay, so this is basically what I told you, and if you know these tricks or you know these relationships, solving a dual or doing any problem that you're given, if you're asked to solve a dual, you can just use these techniques to quickly get your solutions. Okay, now let me okay, this question: what happens if you replace delta by minus delta? Again, you can try it at home. Just do minus delta, solve the constraints. You would see that the sign just changes. Okay, but this doesn't mean that your dual solution, optimal solution, will be -3. Please keep that in mind. Optimal solutions cannot be negative or cannot be negative. They are non-negative. So either y1, y2 will be basic variables with some positive value, or they will be non-basic variables, which is equal to 0. Okay, keep that in mind. Okay, so now we just get to the last point, last topic of today's lecture, and this is this topic, which is again, we talked about all this just to get to this point, okay? And this is very interesting. I think this is the most interesting part of it. The simplex method not only finds the solution to the primal, okay, but also solves the dual, which we did not know till now, okay? The optimal solution to the dual are the negative values of Cj minus Zj, which we saw earlier, and I'll tell you, I'll remind you what it was, under the primal slack variables in the final iteration. Keep this in mind. Final iteration, primal variables, okay? And the negative value of Cj minus Zj. Now let's see what this means using this example. Say we use our classical example again. This is maximize this objective function, 2 constraints, and this is our primal problem, right? Just to remind you what we are talking about, look at this equation. This was the primal that we obtained. This guy, yeah, this. So the solution to this was, for the primal was 2, 3, 27. For the dual was 3, 1, and 27. Keep this in mind, 3, 1, 27, dual, okay? V1, V2 are the slack variables or surplus variables in the dual problem. U1, U2 are the slack variables in the primal problem, okay? Now with that said, let's go back here. I have this problem. I put it in my simplex table and I solved it. How do you solve it? You add, well, actually over here, X3, X4 are basically the same as U1 and U2, okay? Replace this with U1 and U2. Before we used to add X just in order to solve it in the very beginning when we were talking about simplex method, but now to show where this complementary slackness condition actually plays a role, this X3 and X4. So basically what it means that I had X1 plus X2 plus U1 is equal to 5, right? So this is the X3 that I had here, and 3X1 plus 2X2 plus U2 is equal to 12. So the U2 was this X4, okay? So I'm just replacing it just to be consistent with these notations that we have used for complementary slackness condition. And I have X3 as X4, so if I put U1, U2 is equal to 0, okay, I would get X1 and X2 I'm sorry, no. In the beginning, when you want to start, what you do is you put x1 and x2 is equal to 0. So you would get your values for u1 and u2, okay? And you could solve it. So this would be your basic variables, and this would be your non-basic variables, right? I'm sorry, this would be your non-basic variable, this would be your basic variables, all right? And then you fill in this table. So you had x1, 1, this was 1, 0, 3, 2, 0, 1, okay? This is 1, the next one was 0. And the right-hand side would be 5 and 12. And this theta, I told you, is the division, right? 5 divided by 1. So then what you do is you calculate Cj minus Zj, okay? So, and then that Cj minus Zj would be this table over here, this row over here, which is 6 and 5. And 5 and 4 is basically 5 divided by 1 is 5. This 5 divided by 1 is 5. 12 divided by 3 is 4, because we are choosing this column, right? And this was step 1 of our simplex method. And what I want to emphasize on is the last step. That means this last step. Okay. In this last step, we see that now in the Cj minus Zj row, everything is negative. So we stop, we cannot continue. Okay. And when we stop over here, pay attention to this value. These values, they are in which column? Column of U1 and U2. Okay. And pay attention to these two zeros. How about that? Isn't this cool?
Crazy.
This is crazy. Exactly. That's a good word. So what I'm saying is that now in my final solution, x1 is 2, x2 is 3. So this is my optimal solution for my primal. I already got z value, but I don't have to solve the dual again. Because if I look over here, the negative, I told you to pay attention to this, right? The negative of CJ/ZJ. The negative of CJ/ZJ, that in minus 3, if you take multiply by minus 1, it will give you 3. Minus 1 multiplied by minus 1 will give you 1. So the negative of this value would be the optimal solution for y1, y2. And these are also under my u1, u2, which were my slack variables in the primal. So now let's do this. So x1 times v1, x1 means 3, times v1 would be equal to 0, because v1 is, sorry, this is v1. I don't know how I did this. I need to slowly, Let me just do it again. So this was my u1, this is u2, okay, forget this. This u1, and this is v1, this is v2, the zeros. Okay. So x1 is, x1 is 2 times v1, which is 0. So it satisfies the complementary Sackless condition. x2 times v2, again, correct. So it tells me that x1 and x2 are the basic variables, and v1 and v2 are non-basic in the final optimal solution. Then you go under u1 and u2. u1 and u2 in the end, you will see is equal to 0, 0. And the values of under there, the final values in this row of Cj minus Zj would be y1, y2. So y1 times u1 is 0. 3 minus 0 is 0. 1 times 0 is also equal to 0. So this again satisfies the complementary slackness condition. So in the last iteration of the primal simplex method, okay, you will also get that solution for your dual. And you would also know what are the basic and non-basic variables. Isn't that crazy, as our friend said? This is it. So this is basically all you need to know. And please practice this. In the lecture 7 supplementary, there are some examples, work them out, and you will see all of this in play over there, practice. On Tuesday, you'll be having a quiz on this topic itself, so make sure you study. This, if you write this in the matrix form, actually number of what we say computation reduces, but we will just skip it. I've just put this here for your information. If you're interested, you can just search this and you will see how it works. But that's not what we'll be looking at. Instead of doing it in the simplex in the table simplex form, There's a way to do it in the matrix form, but that would take more time. And that actually, since we know already how to solve in simplex, so we do not know how to do. We do not need to further look into that. But there's another way using matrix method, and it would have lesser number of computations. So this is just for information. Okay, any questions?
No questions.
Good. Yes.
By the way, if we like solve the dual form in the simplex method, would the
Exactly.
answer x1
Yes. Yes.
be negative, right?
Yes. You will. The last iteration will give you the solution for the primal. Okay. Yeah, it's just so basically, as I said, to find a dual, the reason why we need to find a dual is sometimes it's very difficult. So if you have large number of constraints in your primal and very few number of variables in your primal, it would be very difficult to solve using simplex method, or even to program it. It will take a long time. So what you do is just find the dual. So solving an LPP problem, what is the best? It would be best, or what I say, time-wise, it would be more computationally efficient if you have an LPP problem which has lesser number of constraints and lesser number of constraints in general, okay? So we try to find a problem which has lesser number of constraints. So if a primal has large number of constraints, we know that, and you know that by converting it into its dual, the number of constraints reduces. Do that and solve the dual, and in the last step of the dual, you will actually get the same solution. Okay.
Okay.
Good, great. So pre-practice the supplementary, because I've already solved it for you guys. Look into that, and your quiz will be on Tuesday. Again, you will have the questions on Moodle. You'll solve it and upload it, and that's it. Okay. And then afterwards on Thursday, we will have our next lecture. Okay. If there are no questions, we can end.
Thank you.
Thank you, guys.